Hello everyone, this is the second video on the 3-wire control. On this video, there's a very important concept I want to talk about. It's the fail-safe design on the 3-wire control logic. So let's look at here. The nature of electrical circuit is such that the open failure. So open failure, that means sometimes the contact is broken on the switch, or the wire connections between the component and PLC, or the coil, the relay coil itself is broken down, or the fuse blow. So those failures we call the open failures. Yes. And this kind of failure is statistically more than likely to occur than any other type of failure. So with electrical circuit design, we need to keep in mind, so this type of the open failure, this is very likely going to happen in the system. So we want to have some sort of fail-safe design in the PLC with everything in that nature. So there are two following safety concerns regarding the 3-wire control ladder logic. So in the first part of the 3-wire control lab, we designed 4 different routines. Right, we finished those design, but now we need to look back to regarding this the fail-safe design concern. So we need to consider both of them with 4 different routines we just designed. The first situation over here, if the wire connecting the stop button with the PLC input is open, it is impossible to stop the motor when the stop button is pressed. So that means once you start the motor, and after you start the motor, and the wire connect the stop button to the PLC, it's open, it's broken, or something happened on there. And if the operator press the stop button at this moment, will the design be able to stop the motor? So that's the safety concern. Situation B, if the wire connect to the start button with the PLC input is open, and we don't want the motor self-start even before the start button is pressed. So what happens is, when the wire connecting the start button with PLC is broken, and even nobody touched the start button, nobody pressed the start button, the motor will start by itself. That's a sort of self-start situation, so we don't want that happen. So in this chart, we'll look at those 4 routines. Do we have the safety concern, either A or B? All right, so let's look at routine 1. So we can go back to the design over here, routine 1. So routine 1 over here, with the routine 1, you can see here on routine 1, PB1 is stop button. So that's right down here, stop, that's PB1. And that's start. Start button is PB2. Okay, so let's look at the start button first. So it's a nobly open push button. So if we have a broken wire over here, something happened, this connection from the button to the PLC is broken. With the broken wire, PB2 will get value 0, no matter what. Even that when the button is pressed down, it's closed here, but will never connect into PLC. So PLC will read 0 all the time. And with the value 0 on here, with the value 0 here on the design PB2, this instruction will always get logic false. So it will never start the motor. In this situation, with the start button broken or the wire connection broken, and the motor will never get started. So this is the first concern. We don't have that. Now let's look at the stop button. With stop button, if the wire broken over here, and the tag value on PB1 will always be 0. With value 0 on here, the exam on instruction will always get false. So this guarantee the motor will never start. Even that motor start before by the start button, the moment when the stop button being disconnected from the PLC, the motor will become de-energized because this logic false. Okay, so that's okay here. So that means for routine 1 we don't have any of this problem. So we can just write down none. So that means either A or nor B is the safety concern with routine 1. And let's look at routine 2. So if both buttons are normally open, let's see what happens. So let's look at routine 2. Go down here. So both buttons are normally open. Let's look at this situation. Oh, okay, I forgot to draw this connection here. So with this is the design. With this design, this is the stop. And this is start. So the design with the problem may have problem with the routine 2 is over here the stop button. So if we have the disconnection happens on the stop button with PLC and nothing going to the PLC, the tag value on PB2 will become 0. And with tag value 0 on here, this exam off instruction will get true all the time because it's value 0. And the problem with this is when the moment the operator tried to press the stop button and make it close, and the design is the tag value will change from 0 to 1, and that will change this instruction from logic true to logic false, and then disconnect and then de-energize the motor. But the problem is with this wire being disconnected, even when the stop button is being pressed down, nothing going to the PLC, so the tag value will become 0 all the time. With the 0 value, this instruction becomes true. You will never be able to stop the motor. So if we go to the other chart, so with this one, the problem is the concern A. If the wire connecting stop button is open, it's impossible to stop the motor. So that's safety concern A. Here. And let's look at the routine 3. Stop is normally open and start is normally closed. So it's totally reversed from routine 1. Let's look at the design. Routine 3. So stop button is PB3 is normally open. So this is stop. And PB4 is start. This is start. And let's look at the start button first. So start button is normally close push button if we have disconnect here. With disconnect on the start button, and the tag value becomes 0. And that will change this exam off instruction become true right away. So you have true right away. That simulate, that's the identical result with the button press. So if nobody press the stop button, the motor will be energized right away. Even though you didn't press start button, just because the wire broken here, that changed to value 0 and exam off become true, and that was true at the beginning, the motor will start. So you will have the self-start problem with this design. So go back here. We have the wire connected to start button is open, the motor will self-start. So that's B in there. Let's look at A. Right. So if this design has the problem with the safety concern A, safety concern A is with the stop button. Stop button is disconnected. Right. When the stop button disconnected, and this one become 0. The tag value is 0 all the time, and then with this tag value 0, this exam off will become true all the time. And if the operator try to press stop button to make the motor stop, it won't do it, because even though it's being connected on here, because wire broken, the 0 will never be changed. So this is true all the time, and this is true, and motor always energized. So as you can see on here, with this routine 3, not only we have problem B, also we have problem A and B. So we have the routine 3. So let's look at the routine 4. Both buttons are normally closed. Routine 4, both buttons are normally closed. So both buttons normally closed, and you may already understand this process. So with this is the stop, this is the start. So start is a normally closed push button. So if something happened to this connection that become broken, PB1 change to value 0 right away. With value 0 on here, exam off, give you logic true. That's the equivalent to press the button. Even though nobody pressed the button, because the wire broken, that's the identical to press the start button. Then if nobody pressed the stop button, the motor will start right away. So that's the safety concern with the routine number 4, and with the stop button, with the start button. So that's B. So that's the this part of the concept I want you to pay attention to, the fail-safe design. All right. Okay, so 0 on PB1.